Oh my goodness, there's a tornado of convergence and divergence and derivatives and integrals and series. Oh my goodness. This is what I like to call the alternating series test tornado. This is how it works. We start over here at the beginning of the tornado. Well, perhaps this is the beginning, but for us, it's here. And let's call this a value of 0. We'll add the first term of an alternating series test. So let's start with the alternating harmonic series, which means the first term is 1. Let's call it u sub 1. U sub 1 is 1. That means when we get to the right edge of this tornado here, that means we have a value of 1. So if this was like the x-axis down here, this would have a value of 1. Then the next term in the alternating harmonic series is negative 1/2. Now, it's not to scale, okay, it's not perfect, but basically we're moving now from this point, we're going left 1/2 unit. So the partial sum so far is 1/2. And then the next term in the alternating harmonic series is u sub 3 equals positive 1/3. All right, so then we're going to move to the right. We're going to get to the right part of the tornado. So 1/2 plus 1/3 is, so we got 5/6 here. All right, then we keep going. We keep going until infinity. U sub 4 is negative 1/4, and you start to get the idea, right? So we go to the left, negative 1/4, go to the left 1/4 of a unit, and then we go right, u sub 5 equals 1/5, and we keep doing that. And the final result is what we would call simply L. It's that value that the alternating series converges to. And what's happening here is basically the alternating series tornado is closing in on the limit, the ultimate value that the alternating series is adding up to. So we have a larger positive term and then a smaller negative term, and then a smaller positive term, and smaller negative, smaller positive, smaller negative, and then it eventually becomes one value. Okay, let's talk about the actual requirements for the alternating series test. Similar to what I presented to you, we basically have a series that has these terms, and we're calling them u's here. So the first term is positive. Well, actually, all the terms are positive. It's just that the sign alternates. So we start with a plus, minus, plus, minus, plus, minus forever. And so that means that the actual term u1, u2, u3, all these terms themselves are positive values. It's the sign that's alternating. And the part of the series that actually is giving that alternating sign is the negative 1 to the n plus 1. Notice that if we just had n, we'd include even numbers, so n plus 1 makes it odd. Every other term negative, basically. Okay, I think you get it. All right, the first requirement is that each u sub n is positive. And again, that's like the actual term. Okay, then the second requirement is that u sub n, and it's a little bit tricky, not that much, but u sub n is greater than or equal to u sub n plus 1, meaning the next term, u sub n plus 1, is less than or equal to u sub n. And usually they're equal. Sometimes the first two terms could be equal, kind of like a Fibonacci sequence. It's 1, 1, 2, 3, 5. And then they start to decrease after that. And then what this means, it says for all n is greater than or equal to big N. That means if we start at big N, call it 1, then this must be true for all n's greater than that 1. So we're just starting at an arbitrary big N, whatever we choose or whatever we're given. And then the final requirement for this is that the limit as n approaches infinity, little n, of u sub n equals 0. Now don't be confused, just because we have something that says 2, that these terms are getting smaller, that doesn't mean they're always getting smaller, or that doesn't mean that 3 is actually true. All right, so we need both of these steps in here. So if all 3 of these are true, then the alternating series test converges. Let's talk about a truncation error. So basically all that I just shared with you is the first part just the only thing about the alternating series test. And then what we're going to do here is we'll talk about the error of the test and do an actual example with the harmonic series. All right, the truncation error. If we're talking about the nth partial sum, all right, we have to talk about something finite because we can't just go forever. But if we're trying to figure out like how accurately does a finite sum represent the infinite series, we talk about the truncation error. So fairly basic. The truncation error for the nth partial sum, so if we're going up to 50 or 75 or whatever, for the nth partial sum is less than, so think about that alternating series tornado now. So it's less than the next term, basically, u sub n plus 1, the n plus 1th term, or the n plus 1st. The n plus 1th term. And basically there's one other little thing that holds true, and it's this: it has the same sign as u sub n plus 1. So what u sub n plus 1, that's the first unused term. And you know, if I were to ask you to think about this, you probably could have figured this out on your own, that you know, we're trying to approximate this alternating series. Well, how close are we to doing it with a finite list of numbers, a finite sum? Well, we're as close as we are to what the next term would be. And basically what this is saying is, look at your alternating series tornado. If you're trying to find out how good the approximation is up until u sub 3, you know, add up the first 3 terms, well, the error is going to be less than this negative 1/4. It's going to be less than that, because that's the amount that we're kind of bouncing back. Now we know that maybe it's going to be somewhere close to half of that, or we're kind of bouncing around this middle point with that value, but it's not necessarily half. All right, let's apply this to an example. And the example is this: that to prove that the alternating harmonic series, that means that we have this p value that's 1, and it's alternating, changing signs. And then we're going to find the error for n equals 99. Like if we add up 99 terms, how good is that approximation? Okay, the alternating harmonic series. So basically we have something like 1 over n. That's an alternating, well, that's not alternating, but that's the harmonic series. It's basically 1 over n to the 1. And there we go, that's better. That equals this: 1 plus 1/2 plus 1/3 plus 1/4. And let's check what the requirements are for the test, okay? So we'll go back here. Each u sub n is positive. Okay, great. Even if I put a negative in between those would still be positive terms. Check. Now the next one is that the values are getting smaller. The terms are getting smaller in size. So they're getting smaller, not by much, but a little bit smaller. So that's good. And that the limit as n approaches infinity is 0. Eventually, are we going to get 0? We're going to get 1 over n, right? So we have 1 over n, and the limit of that approaches 0 fairly slowly. That's true. So we could use the alternating series test. And again, this is called harmonic right here. This is the harmonic series. Fun story, you could look up why it's called harmonic. It's pretty cool. All right, but what we officially have for the alternating series is we have n equals 1, and we go up to infinity, and we have negative 1 to the n plus 1 over n. This is what our official alternating series looks like, and that would give us these values: 1 minus 1/2 plus 1/3 minus 1/4. And by the AST, it converges. To what? I don't know. But I would like to pause this regularly scheduled program to bring you a message from our sponsors. They would like to tell you that the harmonic series, sponsored by music, definitely diverges. But the alternating harmonic series converges. Basically, because the positive and negative values are undoing each other in that situation. Now, back to our regularly scheduled program. Thank you. Truncation error. What is the 99th term? So back at the beginning I said find the error for n equals 99. So the 99th term is 1 over 99. And the 99 plus 1th term, the 100th term, is 1 over 100. And all that's telling us is that the error is definitely less than 1 over 100. Oh, and I think this should be negative right here. Yeah, because if I plug in, let's take that 99, negative 1 to the 99 plus 1 is an even number. So that would give us, oh no, actually, so that would be, oh, no, okay. This would actually be 1 over 99. And then this one would be negative, the 100th term, so negative 1 to the 101. So this would be negative 1 over 100. But we don't really care that the error would be positive or negative. We know that the error is less than this amount. So it could be off by a negative less than that or a positive less than that. And that's it. Let's wrap this thing up. Last little note, and if you have a little more space to just add this in absolute and conditional convergence, just basically going to talk about this for a moment. Because the alternating series, the alternating harmonic series is convergent, but it's not absolutely convergent. Recall, in yellow here, the harmonic series diverges. So that's the positive version of the alternating harmonic series. Because that positive version does not converge, we call it conditionally convergent. So back when you first learned about absolute convergence, there's a little bit of like, oh, I'm not sure what this really means. And all that really means is that the absolute value of that series is allowing it to converge. It's helping us to get to that point. Now we have the other situation in which it's conditionally convergent. And it's just a really great example of it. So again, the harmonic series, p equals 1, is convergent. Divergent. Look back at it. Harmonic series is divergent, and the alternating harmonic series is convergent, and that allows us to make this conclusion. So that is the best and most clear comparison between absolute and conditional convergence. All right, thanks so much for watching.